Yes, hi. I just wanted to say beforehand, Chris, do you mind? Just want to say those student presenters before lunch, it was incredible, like distressingly good. So thank you very much for that, for making me feel like a huge imposter doing what I do. So Apex, just curious, show of hands, who here is using Apex? That's about what I thought. Who here is Apex curious? Yay, this is the right presentation for you. Okay, so what I wanted to talk about was sort of mental models. So if you look at, say, SOPs, people kind of understand that SOPs is points and attributes, DOPS is that plus time and forces, COPS is pixels, blah, blah, blah. And the most recent, I guess, kind of new concept for Houdini in my brain was kineffects, which was points and attributes and transforms. But then, so just to kind of talk about that more explicitly, this is, a sort of a typical kineffects showy thing where you've got points that have a transform attribute and the lines between them express the parent-child links, and kineffects knows how to move the child joints based on the parenting, so you get this curl-up thing. So it's lines and points, that's pretty simple. But then along came Apex, and it was all these scary-looking screenshots and lots of, slightly mixed messaging from the demos. And what I was kind of looking for was what was the core mental model, and I couldn't quite visualize it. So to get to that, we're going to dig a bit more into kineffects itself, understand some of the issues it has, and what Apex is trying to solve. So here, again, just to focus on this thing, I can go from 8 joints up to like 400 joints, and it all still stays pretty fast, and that's fine. But if you sort of imagine that like those 400 points represents, say, the 400 joints of a character, and then if you have, say, 3 characters on screen, performance plummets. Now, this is like a really sort of contrived example, but you can see this is dropping down to like sort of 1 frame a second. It is very contrived, it's faked, but it's proving a point that kineffects has sort of a fundamental performance issue. But if I do the same demo using Apex, it runs at 60 frames a second pretty comfortably on this little MacBook. So this summary is kineffects is slow, Apex is fast. Any questions? No? Okay. But why is it so slow? So we just focus on the rig pose for now, especially just on the rig pose parameter pane. That can explain some of these issues. So ultimately what we're doing is there's a lot of dynamic work. So you can see that the fact that we're using this multi-palm, so we can have X many multi-palms. I'm using an asterisk in the group field, so I can have an arbitrary number of joints being called per multi-palm. I'm running an expression, which is also like a no-no for getting performance. So after the rig post has to like sort of calculate what it needs to work on based on all those inputs, it has to start from the roots, rotate that by a bit, update all the children, go to the next joint, rotate that, update all its children, and so it goes until it completes the chain. All that open-endedness really slows it down. In fact, the rig pose node itself, from a bit of sort of backroom gossip, it's doing a lot of clever tricks under the hood to make it as fast as it is, but there's actually more going on than just that. So there's the overhead of SOPs itself. So Houdini ultimately is optimized for millions of points where each SOP is doing a certain amount of work. When Houdini is cooking and it's moving data between each SOP node, that takes a certain amount of time. Now, usually when you're working with, say, huge numbers, which you often do in Houdini, so if you have like, say, 20,000 points here, copying cubes and things, that's running at about 20 milliseconds a frame. So it's like 10 frames a second. And you go, great, that's fine and fast. You don't question it. But if you look at, say, this kineffect setup over here, which is running at 50 frames a second, and you go, oh, that seems fast. But that's only 36 points, and that should be running like way faster than that. And it's also a question, I guess, of kind of scope, which is that if you're an effects person doing this kind of thing, you go 10 frames a second, awesome. But if you're a character animator and you can't get more than, say, like 10 frames a second out of your sort of proper production rig, you're going to start to have questions. On top of that, you have this question of this simultaneous design and execution problem of your rig network. So here we've got all these kinefx nodes that all represent rig elements, but you can see that they're all time dependent. So each node has to cook its results before the next one can do its thing. So the kind of analogy here is, if you imagine in Maya or Blender, if you use any of those sort of auto rig systems that take like, between say 5 seconds up to 30 seconds to run, this is the equivalent of making a full auto rig on every single frame. So it's constantly being destroyed and rebuilt every frame, which by those metrics, it's kind of amazing that kinefx is as fast as it is, but it's not a long-term solution. So what do we have to fix? So we've got to fix the overhead of all these dynamic inputs. We have to fix the overhead of the SOP's cooking engine. We have to separate building the rig from running the rig. So ideally, you build it once, and then you run it once. You don't build it and run it every single frame. But you also have to keep this sort of Houdini proceduralness. So it's a bit of a mixed bag of problems. So back to the rig pose thing. So let's see if we can kind of mock up what we would need to do to make this go fast. So here's kind of a faked version of doing that. So if we can so rather than having a sort of a wildcard for each joint, if we could explicitly say, this is a joint, this is a joint, these connections are meant to represent parenting between them, we would be running this all inside some sort of compile SOP so that it only kind of runs once. There's no multi-palms. We've removed any of the expressions. And ideally, we do all this work upfront once, and then we just run it. So that's what we're sort of trying to hit. So here's Apex, and this looks scary and weird, but if I kind of show what it's doing, it's basically doing what I just sort of outlined in my faked previous screen demo. So you can see that we load the rig, each of these nodes represents a joint, the connections between them represent the parent-child links. This is applying rotations to each joint. All those things get pushed back onto the rig, and then we write it out. So it's being very explicit. And note that this looks like VOPs, or like a material builder. So all the parameters are exposed, and they can all be wired together. So if we look really close at this, we can see that like a sort of a dumb way to describe this is that its SOPs turn sideways. So you can see that all the parameters that might be required on a transform SOP, they're all exposed as attributes here on this Apex node. All the possible connections are exposed and can be wired together, meaning you don't need any HScript anymore, which is another thing that we wanted to get rid of. It potentially looks more complicated in the wiring, but the core structure is cleaner. There's no SOP engine and a separate HScript expression engine. There's no separate Vex engine. There's no separate Python engine. It's just connections. So we've unopen-ended the rig pose, but this is Houdini. We want proceduralism. We don't want to be sort of manually hand wiring all these nodes together. What can we do? So one possible answer, we could do something like they do in Maya and Blender, where we use Python auto riggers. Maybe we could change the cook mode to manual. So we would force the cook down to manual mode, build all the nodes, turn it back on again. Not very elegant. We could use compile blocks, which is used elsewhere in Houdini. But Apex decided to have another solution for this, which is this big, strange new idea, which is if you take the core concept of Houdini being points and attributes, but you now treat your actual SOP nodes themselves, or Apex nodes, as points and attributes and lines. So you can see here that what I've actually got is if I move nodes in the Apex graph, they update in geometry. If you delete connections, you delete lines. So if you think of it, this view down here in the corner, it's almost a trick. It's like sort of a faked filter where that's the real geometry, and this is kind of pretending to show you what you would see if you were Apex. So the other kind of labored analogy I have is it's similar to building up vellum constraints, where you add shapes and you make constraints and properties and you make all kind of lines and stuff, but nothing actually does anything until you actually run the solver. And here, nothing actually does anything until you feed this into the Apex engine. So the upshot of all this is that when you build a full production kinefx rig, that can be very slow because it's all cooking live. This is all just lines and points, so it's really fast. So if you use like, connect to adjacent points, find shortest path, all those kind of nodes in regular SOPs, you know that making lines and points is what SOPs does really well. So what that means is you could get to this kind of thing where it's almost procedural SOP network generation. So what this is showing is that I can make an Apex sort of rig adapt to any of the inputs, and it's super fast because nothing's really being calculated. It's just making points and lines, attributes, and it's joining them. So what's actually going on here is I've got a line which is sort of representing my joint chain, and as I increase the number of points, I'm making Apex nodes adaptively, and it's all super fast, super real time. So how do we make those lines of points? So the first thing that you need to do is you have to make an Apex network view, which is hidden inside the regular panel thing. So new pane type, and go down to animation, and then Apex network view. There it is. But then how do we actually make them? So you've got a few ways. You can work directly in that Apex network view, or you can do tricks with lines and points like you used to, or there's a few other ways, which I'll explain. So the manual way. The Apex network view, if you put down an Apex edit graph SOP, then you can just make nodes directly. So this is almost like you're using like regular VOPs. So you put that down, you tab in here, and you can make nodes, and you can connect them up. It feels very much like VOPs, so it's pretty easy to pick up. And just to like really kind of drive the point, because this is an important sort of mental model to have. So you can see that while the Apex view looks like it's all these fancy looking nodes with all these fancy properties, the geometry spreadsheet shows you what's actually going on in terms of what SOP sees, which is just literally it's points that have a callback attribute and a name attribute. And I don't think I jumped over to the vertex view, but the vertex view stores the lines, which is just connections between things. So it's all relatively straightforward. And so what we can also do is, now that we kind of know that that's what happens when you use the Apex edit graph, you can do that manually. So I should have made that text bigger, sorry. So we saw just before in the geo spreadsheet that it uses @callback and @name. So I was curious when I was learning all this, saying, well, can I just make an @callback and see what happens? And it totally works. So I can use the same name, so @callback equals transform object, and it makes the nodes. You can make @callback be whatever you want. So at some point here, I just type meaningless characters. And Apex goes, yeah, sure. It doesn't care. So you can see that's all like real things. But if I change it, do I change it? They're looped. Maybe it's the next one. Anyway, the point is, the other important factor here is that the p.x and p.y become the x and y location in the graph. So again, it's just points and attributes. So just to really kind of push that point that this is all just an illusion, you can put that @callback attribute on whatever you want, and the Apex graph will just happily interpret it. So note how, again, like I can do it, and the graph just happily keeps up. Because again, it's not calculating anything, it's not cooking anything, it stays really fast. People have done these kind of tricks using VOPs or the material editor, but it gets very slow because they are inherently doing work. They're trying to compile the network every frame, whereas this thing, it's just a faked filter view. So pushing this idea even further, we can try and construct the same rig pose equivalent from before. So we can make a few more nodes, can set more callbacks, and we can see the graph kind of build up as I'm building it all just in Vex. So I think this is the point where I do a dummy name, and it does make the node. Apex doesn't care, so it doesn't actually give you sort of any warnings or errors. It just assumes that you're an idiot and you'll pay for your mistakes later. Okay. And so here's how you do the entire graph that I did before. So you can see that while doing kind of simple, representing nodes with that callback attribute is easy. Once you start to make these slightly more complicated wiring chains, Vex is not ideal for this. So it's totally possible. I have proven the point that you can make Apex rigs purely in Vex and it's fine, but it's not fun. So the last part of all this is then how you actually run it. And the answer is a invoked graph. So what feeds into it is your collection of points and lines becomes the first input. Anything that's meant to be running on, which in this case would be my skeleton, is the second input. And also feeding into that would be any other sort of animated parameters. So in this case, I think I've got time feeding into it as well. And so that combination of the rig logic as the first connection, the joints for the second, animated parameters for the third, and you get moving things. So, as I said, Vex is not great for this. So we need a way to refer to nodes and properties. Vex isn't great for that, but Python is really good for that. So this is doing the same thing. So don't worry about the actual thing. You can't read it on the screen anyway, but you can see that Vex is quite sort of long and complicated and lots of sort of repeated boilerplate. But doing it in Python, it's shorter, cleaner, more elegant. So that's not bad. But side effects figured that they could go one better. So that's what Apex script is. So Apex script is basically Python with frills. And it's optimized for making node graphs. And it looks and feels and tastes very much like Python. So if we were to compare these two scripts, so this is sort of almost vanilla Houdini Python on the left, and this is Apex script on the right. And you can see that it gets even more elegant. Looks and feels and tastes like Python, but it's much cleaner for making node networks. Plus, and so I guess what I want to state as well is that because riggers use Python a lot, it kind of made sense to do this like sort of flavor of Python made for riggers. You're still totally free to use Vex or use manual wiring, but side effects putting a lot of effort into Apex script. Plus, Apex and Apex script have some more tricks, which I'll get to shortly. So, recap. We've swapped all the open-endedness of kind of like SOPsy ways of doing things with this way of being very explicit. We can design networks using points and lines. We can make those points and lines in several different ways. But let's get back to some high-level questions, which like, what is needed to make a rig? So obviously, transforms and IK solvers and constraints. But if you really think about it, you know, a full production rig means all these kind of things. Now you've got handles, and you need to be able to change colors of stuff. You need to give feedback to the user, all this kind of stuff. I mean, really, what you need is kind of all of SOPs available down here in this Apex context, right? So that seems like a really big task. You know, there's no way Apex could possibly have all of SOPs available down Apex, right? Oh my God, it does. There was this effort a couple of releases ago, which is called SOP verbs. I kind of heard the term, didn't understand it, sounded kind of complicated and high up. It seems that Apex was able to magically sort of hijack that and kind of ride on the coattails of this SOP verb effort. So they've actually got all these nodes available in Apex. So you probably can't read it, but here you've got like SOP attribute promote, SOP file, there's a SOP box, like almost most of the nodes you would expect to find in SOPs, they're all available as nodes in Apex, which is pretty powerful. So just to kind of like really prove the point, again, I was trying to eat my own dog food here with this demonstration. So, you know, the usual kind of idea of, you know, you want to have like a box, you want to scatter points on it, you want to then copy geometry onto the points, and you want to set up attributes on the points. This is, like I said before, SOPs sideways. So starts at the box, goes to a scatter. This is a little loop to add attributes. You know, I'm changing properties of the scatter. It's SOPs. It's SOPs in Apex. Ooh, scary new worlds. You can even do Vex, which I found surprising. So there is this node, the SOP attribute vault. So you can see here that basically this is the SOP equivalent on the left with a bit of a Vex wrangle. I can take that code and I can directly paste it into this one parameter down here in Apex, and it just works. So this is a pretty handy sort of stopgap solution. If you are kind of pouring through Apex and you go, oh man, if only I had a wrangle, I could solve this thing. You can do that. It's all there to do. It's not advised. And I think part of the sort of the design intent for Apex is that you have a single execution engine, which is Apex itself. Because this is now combining Apex plus Vex, you're kind of mixing your peanut butter and your jam. Don't do that. But it's possible. So if you look at the full set of Apex nodes here, there's all the SOP stuff that I mentioned before. You've also got atomic operations like add and subtract and mults like you do in VOPs. You've got some motion editing tools like you'd find in shops. There's been a few requests over the years that that Houdini has like too many contexts, so we need one sort of master unifying context to rule them all. I mean, Apex is kind of becoming that, which is pretty cool. So we have lots of nodes available. We know that there's this Apex script language. How do we use it? So don't get too distracted by the bitsy points here. But the first time that I tried to use Apex scripts, it wasn't very interactive. Henry Dean and Esther at Side Effects gave me some clues. So these are the things you need to change. So when you put down this Apex script node, you have to change. You have to make sure the headers are enabled, and you're in graph mode. You have to open invocation and enable the input to read from geo, so you can so that basically data which is flowing into it, you can grab it, modify, and change it. And then you have to modify the output to ensure that the nodes that you make in Apex script are written out. And you finally set the visualization mode to the actual output. Easy. Everyone's got that? Good. Okay. There's a point to all that silly boilerplate text. So this is me kind of having done it sort of towards the end of the process. And so you can see that we go from this empty graph, and then once I start sort of making nodes and flip some things, you see nodes appearing down here. So it's live. You know, I can type Apex script up there, and we see nodes appearing down here. So that's cool. But if I go back to what it was before, you get this other graph, which looks kind of strange. So you can see this is also made up of nodes, and they've all got this graph underscore prefix. So this is the other neat trick of Apex scripts. Each line over there is actually represented as a single node over here. So what that basically means is Apex script itself is capable of generating Apex scripts. So it's kind of like metaprogramming. So I can comment out lines over there, and you see nodes disappear here. And it all updates live. And the reason this is the default view is that this is where riggers will probably be spending most of their time, where you're making scripts to build scripts. There's really, really powerful stuff. So I'll come back to this thing in a sec, but let's go back to KineFX for a little bit. So here is a production rig from a KineFX masterclass from a few years ago. It's a pretty cool setup that blends from a four-legged walk to a two-legged walk to a stumble using ragdoll and back again. Now, if you dive inside the rig, you can see there's a substantial amount of SOPs. They're stored as an HDA to set up all the control points, the FKIK, the skeleton blends, reversing of joints, all these tricks. And it's all time-dependent from start to finish. Then it's duplicated for the biped walk cycle. Then it's duplicated again for the blend cycle. And it's duplicated again for the ragdoll. Okay, so it's pretty complicated. And if you wanted to add extra controls in here, you've got to have a pretty deep understanding of what's going on. And remember, this is all being sort of like built from scratch every frame. I mean, it's super duper heavy. Now let's compare that to an Apex auto rig setup. So I'll explain this more in a sec. But the idea is that a lot of that complexity of the KineFX setup is wrapped up in those three purple nodes. So, and remembering what we've sort of talked about so far, these nodes don't do any work. It's just adding lines of points, so they're really efficient. The lines of points to represent that network are built using Apex script templates from Side Effects. And it's only when I actually go to the last node that it actually all gets cooked and compiled. If you put down a scene animate node, which is it's basically a wrapped up invoke, it does the same thing. So that's when it actually gets converted into a rig, and you can pose a character. So if we look at the Apex script network view while we're browsing through these things, we get some more context. So in KineFX, you've got to be really careful about how you design that network, where you're blending FK and IK. What I mentioned before about how Apex contains nodes and functions to manipulate Apex graphs, here you can see it in action. So adding IK, for example, you've got to add nodes at the start of the graph. Apex script abilities allow it to find the correct nodes at the start of the graph and insert what it needs there. The joint deform needs nodes put at the start and end. And you can see that as I change the number of joints, or if I don't tag things, or if I give it input which is varying, Apex just updates the graph in place. So it's properly adaptive auto rigging, but you don't pay the cost of updating every frame, and it's relatively straightforward to change. So how do we build these auto rigs? So this requires a bit of prep. So the first step is you have to pat the character so that the final target is to have the mesh, the skeleton, the control handles, and the Apex rig logic all bundled together. So you do this using the pack folder SOP. So for now, I'm just going to connect the skeleton to the second input, and following sort of some Apex conventions, we name it base.scale. That's enough to keep AutoRig happy. So we can now create one so I can put down a AutoRig and I can set its type to FK transform, like that. And then if we look in the Apex graph, we can see that what it's done is the equivalent of the rig pose. So a node has been made for every joint transform. It's had parameters created so that we can control those rotations, and all these things filter back up so that it puts those changes back onto the rig. It's also made, so it's basically made that sort of, that explicitly defined high performance rig that we're after right from the start. A nice little bonus feature here is that even though before I said that you would only see this run when you get down to the final scene animate, if you get into the viewer state in AutoRig component, it has its own built-in invoke so that you can sort of test it live in context, which is handy. So if we append another AutoRig node, so we're going to set the mode for this next one to be IK, to multi-IK, and we will see no change. And the reason is that the IK AutoRig expects to find attributes on the rig to tell it which joints require IK, and we haven't done it yet. But note that it doesn't error. It just lets the Apex rig flow through untouched. This is by design, so that you can have like multiple AutoRig or Apex script components that add functionality, but only if it finds joints that it's told to work on. So to set up multi-AK, we're going to do that in the form of tags. So the attribute adjust array swap does this. So we add that before the pack. We set its mode to point. We can select all the points on the right leg, and we tap A to bring up a tag editor, and we add a tag called r_leg. We do the same for the left leg. And then when we jump back down to the IK node, we'll see that it will have magically made us IK controls, like that. It's pretty cool. And lastly, we have to deform the mesh. So we can append another AutoRig. We set its mode to bone deform, but hang on, we didn't add the mesh. Stupid. So I'm going to go back to the top, going to wire in the mesh, and we name that base.shape. And then we can jump back down to the final node, and we will see the mesh being deformed. So there it is. So now you're a rigger. Congrats, easy. Okay, you're not. And there's still lots to cover. But hopefully this now sort of bridges you to a place where you can watch a lot of the other video tutorials and read the docs and be not quite so lost. So remember, this is all being actively developed. But let's recap. So to get back to the core question of what is Apex, we should be able to answer it. So what is Apex? It's points and attributes. Those points represent nodes in a graph. An Apex graph can contain rig logic, contain SOPs, whatever you want. And it also lets you contain nodes to modify Apex graphs itself. You can make them in a variety of ways. It only cooks when you want it to, which is one of the most important features. The AutoRig nodes are basically wrapped up Apex script. And this is a big important point, that while the first focus was rigging, other parts of Houdini have recognized the power and the performance of it, so it's starting to leak out into other stuff. So a lot of Copernicus now is done using Apex. A lot of the sort of interactive viewer states are now being sort of ported over to use Apex. So something to keep an eye on. And that's my talk. So I made a point of saying don't look too closely at things, because you can go download them from a site. And I will also say that while I have this now sort of better conceptual framework in my head, I've not actually built any Apex rigs. So if there's questions, be prepared for me to say, I don't know. So that's my talk. Way.
Okay. We have time for 2 questions. So 2 hands.
Yeah, thanks for the talk. So I want to ask if I understand it correctly. So the way that you presented Apex now is it is kind of like an abstraction layer where you can create a network that's kind of like self-adjusting and self-expanding. So you create like kind of a framework like you would make a Python script to create a rig in Blender, like you said, and then it will just like add these nodes like in a network, and it will remain all editable, and it's like not limited to only the rigging. And do I understand that correctly?
Yeah.
Or okay, cool. That was my question.
Hooray.
Thank you very much for the presentation. Impressive stuff. The question, since now we have Apex or graph operators, dare I say, why do we still need SOPs or any other context in that regards?
It's a very good question. I would say that, I mean, obviously we all love SOPs. That's not going anywhere. What this now allows us to do, I feel, and again, I'm not side effects, so I don't know. But it feels like we now have a way that it's happened a lot where you build stuff in SOPs and it gets more and more complicated, and then performance starts to tank, and you go, oh well, I can't fix that. You know, maybe you can find some sort of clever hack, but really you're constrained by SOPs itself. Whereas now we have this option. We go, okay, well, I'm going to take my whole big SOPs chain, I'm going to turn it sideways, feed it into Apex, and now you've got a standalone tool. The other aspect of this whole thing of it being, just points and lines is that now you can have stuff, streamed out on disk. So rather than having HDAs, which are, kind of mini HIVE files essentially that, they're not directly editable outside of it, they can now just be geometry. They can be like sort of, loaded and slung around, very quickly. You've now got ways that you can kind of identify ins and outs of your graph, and you can sort of like insert stuff before, insert stuff after, insert stuff in the middle. It's, stuff that you would normally have to either use Python to kind of hack on it. You can now, it's an analogous, I feel, to TOPS. I mean, actually, show of hands, who uses TOPS? More of you should be using TOPS. Come on, you lazy shits. But TOPS lets you kind of take a step back from your process, and you can go, oh, I've now got this kind of this high level view, and I can sort of control the process from further away. And Apex sort of allows you to do that, but in this kind of high performance context. So yeah, I think it's almost like setting the groundwork for how Houdini is going to have to go over the next 5-10 years if it's going to stay performant.
Okay, thank you very much. Good.